Here's something that sounds impossible, but it's completely true. Right now, this video, the exact one you're watching, is not floating in the air, and it is not up in a cloud somewhere in the sky. Right this second, a piece of it is racing along the bottom of the ocean, deep underwater inside a tube of glass about as thick as a garden hose, as a tiny pulse of light. We call it the cloud. That word is lovely, and it's a lie. The internet isn't a cloud. It isn't really wireless, and it certainly isn't floating in space. It's a physical thing, the single biggest machine human beings have ever built. Millions of miles of cable, warehouses packed with humming computers, and light moving through glass at about 200,000 kilometers a second. So, over the next few minutes, we're going to follow your data on its entire journey, from a computer in a building somewhere, out through the wires, across the ocean floor, and onto the screen right in front of you. Every single step is a thing you could actually reach out and touch. By the end, you'll be able to trace the whole path yourself, and you'll never think the word cloud the same way again. No hype, no doom, just how it works. Let's pull that cloud apart, because the word hides everything interesting. When someone says your photos are in the cloud, here's what that actually means. They're on a computer, a real one. It's sitting on a shelf, in a building, plugged into the wall, drawing electricity and getting warm, in a place you could drive to. Those buildings are called data centers, and they're basically warehouses filled with thousands of computers called servers, stacked floor to ceiling, humming away day and night. There are more than 12,000 data centers around the world, and around 1,300 of them are absolute giants, the ones we call hyperscale. That's where your video lives. The cloud is a warehouse, and it burns very real electricity. So the content lives in a building. How does it get from there all the way to you, maybe on the far side of the planet? Not through the sky. And here's the fact that surprised me most. The vast majority of the data that crosses between continents, roughly 95 to 99% of it, does not travel by satellite. It travels through cables lying on the floor of the ocean. Real physical cables on the seabed, down in the cold and the dark. Satellites carry only a tiny sliver, well under 1% of the international traffic. So when your message goes from one continent to another, it almost certainly dives under the sea to get there. The internet is a place, and an awful lot of it is underwater. So your video is in a building, and it needs to reach you. Here's the first beautiful trick, the idea the whole internet is built on. Your video is not sent to you in one piece. Instead, it gets chopped up into thousands and thousands of tiny chunks called packets. And every single packet gets a little label stuck on the front, like an address on an envelope, saying where it came from and where it's headed. Those packets don't travel together, and they don't wait in line. Each one is set loose on its own, free to take whatever route across the world happens to be clear at that moment. Two packets from the very same video might cross the planet by completely different paths, and then they all get reassembled, back in the right order, at your end. Picture it like this. You want to send a friend a 1,000-page book, but you're only allowed to mail one page at a time, on postcards. So you number every page, drop all 1,000 postcards in the mailbox, and let them find their own way. Some go by truck, some by plane. They turn up out of order over several days, and your friend simply sorts them by number and rebuilds the book. That's packets, and it's genuinely how the internet works, billions of times a second. This idea is called packet switching, and it was dreamed up in the 1960s. independently by two people who'd never met, Paul Barron in America and Donald Davies in Britain, who coined the word packet. And they built it this way on purpose for one powerful reason. If part of the network gets destroyed, the packets simply flow around the damage and take another road, which is exactly why the internet is so remarkably hard to kill. Now, for a packet to find you, it needs to know where you are. It needs an address, and every device connected to the internet has one. Your phone, your laptop, the server the video lives on, all of it. It's called an IP address, and it works almost exactly like a postal address, except instead of a street and a house number, it's a number that points uniquely to your device. And here's a story I love. The internet running headfirst into a very human problem. The original system, which ran everything for decades, is called IP version 4. It's built on 32 bits, which works out to about 4.3 billion possible addresses. Back in the 1980s, 4.3 billion sounded like a number you could never use up. It sounded infinite. It was not. On the 3rd of February 2011, the world handed out the last big block of free version 4 addresses. We ran out. We literally ran out of internet. So well before that day, engineers had built a replacement. IP version 6 made sure it would never happen again. Version 6 uses 128 bits, and the number of addresses that gives you is genuinely hard to hold in your head. It's about 340 undecillion. That's a 3, a 4, and 37 more digits after them. It's so many that you could hand one to every grain of sand on every beach on Earth many times over and still barely make a dent. We ran out of internet addresses once, so we built a system with more of them than there are grains of sand on the planet. Problem solved, hopefully for good. There's one more piece before your packet can set off, and it fixes a very simple problem. Humans are terrible at remembering numbers. You don't type a long string of digits to open a website. You type a name. A word, something you can remember. But your device can't do anything with a name. It only understands the numbers, the IP addresses. So something has to sit in the middle and translate the name you typed into the number the machines need. That something is called DNS, the Domain Name System. And the easiest way to picture it is the internet's phone book. You know the name, DNS looks up the number. And the lookup is a tiny little chain. When you type a name, your device asks a helper called a resolver. What's the number for this one? If the resolver doesn't already know, it asks one of the internet's root servers, which points it toward the servers in charge of .com, which points you to the one specific server that knows the exact address for the name you want. Name to the right neighborhood to the exact number. And here's the marvel. That whole back and forth usually finishes in a few thousandths of a second, and it happens billions of times a day without anyone noticing. At the very top of that phone book sit the root servers, and famously there are 13 of them, named A through M, run by 12 different organizations. 13 sounds alarmingly small to hold up the entire planet, right? But it's a bit of a trick. Those 13 names are actually mirrored across more than 1,700 physical machines, scattered through over 100 countries. Even the phone book has no single point of failure. And you'll notice that keeps being the theme. Okay, your video's been chopped into packets, each one labeled with your IP address, and DNS has looked up the number. Now the packets actually travel. And this next part might be the most surprising idea in the whole video. Not a single computer along the way knows the full route to you. Not one. There's no master map. Instead, the internet is stitched together out of machines called routers. And a router does just one simple job. It looks at a packet's destination and it hands that packet one step closer to the next router in roughly the right direction. That's it. Then the next router does the same, and the next. Your packet crosses the entire planet as a relay race, passed hand to hand by machines that each know only one thing: which way is closer. None of them has ever seen the whole path. Now zoom out, and here's what the internet actually is. It isn't one big network. It's more than 70,000 separate networks. Your internet provider, a university, a giant company, a government, each run by completely different people that have simply agreed to pass each other's traffic along. And that's the whole secret hiding in the name: Internet. It literally means a network between networks, a network of networks. And here's the part people find hardest to believe. Nobody runs the internet. There's no headquarters, there's no master computer, there is no big red off switch, because there's nothing to switch off. It's just tens of thousands of networks, all choosing to cooperate, with packets flowing around any gap that appears. That is not a weakness. That decentralization is exactly why it's so astonishingly hard to break, and why it's held together for more than 50 years.
But hang on, if every packet is set loose on its own, taking its own route with nobody watching the whole path, how do they possibly arrive as a perfect, complete video? Packets get lost, they turn up out of order, sometimes the very same one shows up twice. So how does that mess turn back into your movie exactly right every time? This is where the real teamwork happens, in a two-part team called TCP/IP. We've basically met the first half already. IP, the Internet Protocol, is the part that handles addresses and delivery. But IP is what engineers politely call best effort. It's a fearless courier. It grabs your packet, flings it toward the address, and promises nothing. Packets might drop, they might arrive scrambled. IP just shrugs and moves on. So riding on top of IP is the second half, the hero of reliability, TCP, the Transmission Control Protocol. TCP is the careful one. It numbers every packet before it leaves. At your end, it keeps a checklist, ticking off each one as it arrives. If packet number 400 never shows up, TCP notices the gap and politely asks for that one to be sent again. And once it has the full set, it stacks them all back into the right order and hands you a perfect, complete file. So think of it as a team. IP is the courier who races the packages out and doesn't sweat the details. TCP is the checker at the door, making sure everything arrived and it's all in order. Best effort plus guarantee. And this, quietly, is the big idea behind the whole internet. Split a hard job into simple layers and let each layer do one thing well and trust the layer beneath it. That's how thousands of separate groups could build one internet without ever needing a single boss. Now we get to my favorite part, the actual road your data travels on. And honestly, it's gorgeous. Remember, your packets have whole oceans to cross. They do it as light, not electricity, not radio, light. Inside a fiber optic cable is a strand of astonishingly pure glass, thinner than a human hair, and your data races down it as tiny flashes of light, flicking on and off unimaginably fast. The light stays trapped inside that glass thread by bouncing off the inside walls, over and over, never escaping, all the way to the other end. It's called total internal reflection, and it means a beam can travel thousands of kilometers of twisting cable and still come out clean at the far side. That light moves it out 200,000 kilometers a second, roughly 2/3 of the speed of light in empty space, because the glass slows it down a touch. That's still fast enough to loop the whole planet several times in 1 second. The cable carrying all this light across an entire sea is, for most of its length, only about as thick as a garden hose. That's it, a garden hose on the seabed, carrying the internet between continents. Because the light gently fades over such enormous distances, every 60 to 100 kilometers there's a device spliced into the line called a repeater, which gives the light a fresh boost. And to power that whole chain of repeaters across an ocean, they push up to about 10,000 volts down the cable itself. These cables are laid along the seabed by special ships that unspool them slowly for thousands of kilometers as they sail. And there are a lot of them, more than 500 of these cable systems in service today, adding up to over 1.5 million kilometers of cable. That's enough to wrap around the Earth roughly 37 times. That is the real internet. Hair-thin glass, garden hose cables, and pulses of light, sitting silently on the ocean floor.
So here's a fair question. If your data really is crawling along the ocean floor, bouncing between continents, why does the internet feel instant? 2 reasons, and the first is a genuinely clever cheat. A lot of the time, your data didn't cross the ocean at all. The big services you use every day, the video sites, the streaming apps, quietly keep copies of their most popular content on servers physically close to you, often right inside your own city, or even inside your internet provider. It's called a content delivery network, and the idea is simple. Don't make everyone reach across the world for the same popular video. Keep a local copy nearby and hand it over from just down the road. So when you press play, very often a server a few kilometers away answers, not one an ocean away. The second reason is that light really is staggeringly fast, but it is not infinitely fast. That 2/3 of light speed is a hard floor. No matter how good the technology gets, a signal can only cross the planet so fast because you cannot beat the speed of light. And one honest note to finish, because you may have seen some scary headlines. Those undersea cables do sometimes break. Around the world, there are about 200 cable faults every year. But here's the thing, it's rarely anything dramatic. Roughly 86% of the time, the cause is simply a ship's anchor dropped in the wrong spot, or fishing gear dragging along the seabed and snagging a line. When it happens, specialized repair ships sail out, lift the cable, splice it back together, and lower it home. It's routine maintenance, the plumbing of the planet getting fixed. And because the whole network is decentralized, when one cable goes down, the traffic just quietly reroutes through the others, and most people never notice a thing. The system was built to bend, not break. So let's finish with the one idea that ties it all together, and it's the thing most people get wrong. The web is not the internet. The internet is everything we've just built. The cables, the packets, the routers, the addresses, the giant physical machine that moves data around the planet. The web, websites, the pages you browse, is just one thing that runs on top of it, one service. Because plenty of other things ride the very same internet without touching the web at all. Your email, your video calls, the online game you play, the messages on your phone. The internet is the road. The web is just one kind of truck driving on that road. A hugely popular truck, but only one of many. And this whole machine has a surprisingly precise birthday. The first message ever sent between 2 computers on its ancestor network went out on the 29th of October 1969, and the system crashed after just 2 letters. The modern internet's shared language switched on the 1st of January 1983,
And the web, that one popular truck, was dreamed up by a scientist named Tim Berners-Lee in 1989, with the very first website going live in 1991 at a physics lab in Europe called CERN. And from that, in a single lifetime, we have built a machine that now connects about 6 billion people, the better part of everyone alive, all sharing the largest thing humanity has ever made. And now you can see it for what it really is. Not a cloud, not magic, buildings and cables and glass on the ocean floor and light. A physical thing, owned by no one, quietly holding up the modern world. If you enjoyed taking this apart, subscribe and stick around. Next time, we're grabbing another everyday piece of invisible tech and cracking it open, just like this. No hype, no doom, just how it works. See you in the next one.